In 1972, a number theorist showed a physicist a formula derived from prime numbers. The physicist told him it was identical to the energy spectrum of uranium nuclei. Nobody has explained why. In 1959, John Nash stood before 250 mathematicians at Columbia to prove the greatest unsolved problem in mathematics. His mind came apart before he finished. And in 1866, a man died of tuberculosis at 39, leaving behind 8 pages that have never been proved in the century and a half since. Those 3 moments are the same story. The thread connecting a tea room in Princeton, a lecture hall in New York, and a deathbed on the shore of Lake Maggiore is a single conjecture about where certain numbers fall on a line. A conjecture that controls every prime in existence, verified 3 trillion times, proved 0. Tonight, we are going through all of it. Riemann's 8 pages, Montgomery and Dyson at tea, Nash's unraveling, Atiyah's final lecture, and a 2018 result showing the answer, if it exists at all, is true by the thinnest margin mathematics has ever measured. Settle in, get cozy, subscribe, or join if you haven't. I have a Patreon where we go wider across math, physics, and the history buried behind them. Stay to the end, because the question this builds toward is not whether the hypothesis is true. It is whether mathematics is capable of proving it. Let's start where it started. In 1859, a man who would be dead in 7 years walked into the Berlin Academy of Sciences and handed over 8 pages, not a treatise, not a book, a short memoir written in German with the modest title On the Number of Prime Numbers Less Than a Given Quantity. It was published in the November issue of the Monatsberichte, pages 671 through 680, and it contained a single conjecture about a single line on a graph that would go on to dictate the behavior of every prime number in existence, every prime that has ever been found, every prime that will ever be found, every prime so large it dwarfs the number of atoms in the observable universe. All of them answer to those 8 pages. And in 167 years, not a single human being has been able to explain why. That conjecture is called the Riemann Hypothesis. You have probably heard the name. You may have heard it called the greatest unsolved problem in mathematics. You may know it carries a $1 million bounty from the Clay Mathematics Institute, making it one of only 6 remaining Millennium Prize problems out of the original 7. What you almost certainly do not know is what the hypothesis actually says, why it matters so much more than the prize money suggests, and what it implies about whether mathematics itself has limits that no human mind will ever cross. Because the Riemann hypothesis is not just an unsolved problem, it is a crack in the foundation of everything we think we know about numbers. And the fact that it has resisted proof for over a century and a half, despite being checked against more than 3 trillion individual cases and found correct every single time, is not a reassuring sign that we are close. It is a deeply unsettling sign that something fundamental about the way humans do mathematics might not be enough. I need to be precise about what these 8 pages contained, because the version of this story that floats around popular science is missing the part that actually matters. The surface version goes like this. Bernhard Riemann was a brilliant mathematician. He proposed a hypothesis about where certain special numbers, called zeros, fall on a graph. If we could prove the hypothesis, we would understand prime numbers better. $1 million awaits whoever does it. That version is not wrong, but it leaves out the part that should keep you awake. It leaves out the fact that these 8 pages did not just describe a pattern in the primes. They revealed that the primes, the most fundamental objects in all of mathematics, The atoms of arithmetic are not chaotic at all. They are not random. They are being orchestrated. They are dancing to a hidden score, a score written in the language of complex analysis, and the Riemann hypothesis is the claim that every note in that score falls exactly on one line, not roughly on the line, not close to the line, exactly on it, with zero deviation, across infinity. And here is the part that should disturb you. We can hear the music. We can measure it. We can compute individual notes to billions of decimal places. We can verify that the first 3 trillion notes all fall on the line with perfect precision. But we cannot prove that the 3 trillion and first note will, or the 10 trillionth, or the googolf. We cannot close the gap between evidence and certainty. And that gap has been opened since 1859, and it is not getting smaller. The man who opened that gap did not live to see what he had done. Bernhard Riemann died of tuberculosis on the 20th of July, 1866, at the age of 39, in a rented house overlooking Lake Maggiore in northern Italy, reciting the Lord's Prayer with his wife Elise beside him. He had been a working mathematician for roughly 15 years. In that time, he had reshaped the geometry of curved spaces in a way that Albert Einstein would use 60 years later to build general relativity. He had redefined what it means for a function to be integrable. He had laid foundations in complex analysis that every mathematician alive still depends on. And he had, almost as an aside, written 8 pages about prime numbers that would become the single most important unsolved problem in human mathematics. He published exactly 1 paper on number theory in his entire life. It was enough to rewrite the field forever. But the biography gets darker. After Riemann died, his colleagues in Göttingen attempted to sort through his unpublished papers. This is where the historical record splits into fact and folklore, and I want to be honest with you about which is which. What we know for certain is that Richard Dedekind, Riemann's friend and mathematical executor, recovered what he could and published Riemann's collected works in 1876 with the help of Heinrich Weber. What we also know is that a substantial volume of unpublished work was lost. The popular version of this story, the one that appears in nearly every popular mathematics book written about the Riemann hypothesis, is that a housekeeper in Göttingen burned many of Riemann's papers after his death. The Mac Tutor History of Mathematics archive at the University of St. Andrews, one of the most careful biographical sources in mathematics, records that unpublished papers were lost but does not specify burning. Other sources say discarded. The most dramatic versions say burned in a fireplace. I cannot tell you which version is true. Nobody can. But what I can tell you is this. Somewhere in that lost pile of papers, written in the hand of a man who saw deeper into the structure of numbers than anyone before or since, there may have been notes, drafts, partial arguments, approaches to the very conjecture that now carries his name. We will never know. And the mathematical community has been trying to reconstruct what Riemann might have known for a century and a half. The 8 published pages are all we have. And they were enough to show us a pattern so deep that the entire field of analytic number theory exists to chase it. I want you to understand who this man was, because the contrast between the person and the legacy is something I still find difficult to sit with. Riemann was born on the 17th of September, 1826, in Bresselenz, a village in the Kingdom of Hanover, the second of 6 children born to a poor Lutheran pastor. He was painfully shy, almost cripplingly so. He struggled with public speaking his entire life. He was frequently ill, suffered from what his contemporaries described as a nervous disposition, and lived in poverty for most of his academic career. But he could see things in mathematics that nobody else could see. When Riemann was a schoolboy, his teacher lent him a copy of Adrien-Marie Legendre's Théorie des Nombres, a dense 859-page treatise on number theory. Riemann returned it 6 days later and reportedly told his teacher he had read it thoroughly. His teacher later confirmed that Riemann could indeed discuss the contents in detail. He was 14 years old, 6 days, 859 pages of number theory written for professional mathematicians. He enrolled at the University of Göttingen in 1846, initially to study theology at his father's request, but soon switched to mathematics. He moved to the University of Berlin for 2 years to study under Carl Jacobi and Peter Gustav Lejeune Dirichlet, two of the finest mathematical minds of the era, and then returned to Göttingen, where he fell under the supervision of the greatest mathematician alive, Carl Friedrich Gauss. Here is where the story takes a turn that connects the personal to the mathematical in a way I think is underappreciated. For his doctoral thesis in 1851, Riemann submitted a work on the theory of functions of a complex variable. Complex here does not mean complicated. It means functions that operate on complex numbers. Numbers with both a real part and an imaginary part. Numbers that live on a two-dimensional plane rather than a one-dimensional line. Gauss, who was notoriously difficult to impress and famous for dismissing work that lesser mathematicians considered brilliant, responded to Riemann's thesis with what for Gauss amounted to effusive praise. He called it evidence of a gloriously creative, active, truly mathematical mind and of the most splendid, inventive talent. This matters because 3 years later, in 1854, Riemann submitted 3 possible topics for his habilitation lecture, the final requirement for the right to teach at a German university. Convention dictated that the committee would choose one of the first 2 topics which candidates typically prepared in advance. But Gauss, deviating from convention in a way he almost never did, selected Riemann's 3rd topic, the foundations of geometry. Riemann was forced to develop an entirely new mathematical framework in a matter of weeks. The result was a lecture titled On the Hypotheses Which Lie at the Foundations of Geometry, delivered on the 10th of June, 1854, to an audience that included Gauss himself. That lecture did not merely advance geometry, it replaced it. Riemann introduced the concept of a manifold, a space that could be curved in any number of dimensions, equipped with a metric that described how distances were measured within it. He showed that Euclidean geometry, the flat geometry of parallel lines and fixed angles that you learned in school, was just one special case of an infinitely larger family of geometries. He gave mathematics the language to describe curved space-time 60 years before Einstein would need it. Think about that for a moment. A shy, sickly, impoverished young man, pressured into a topic he did not plan for, delivers a single lecture that will be published posthumously by Dedekind in 1868, and that lecture becomes the mathematical bedrock of general relativity. Einstein did not invent the geometry he needed. Riemann had already built it. A dead man's lecture notes, published 2 years after his death, became the operating system for the most successful theory of gravity ever constructed. But that is not why we are here. The geometry was, in a sense, the sideshow, the achievement that would have made Riemann immortal in any other century is not even the most important thing he did. In August of 1859, at the age of 32, Riemann was elected as a corresponding member of the Berlin Academy of Sciences. This was a significant honor. The Academy had recently been presided over by Alexander von Humboldt and included among its members some of the most distinguished scientists in Europe. It was customary for newly elected members to submit a paper, a contribution to the Academy's proceedings as a gesture of gratitude and intellectual engagement. Most mathematicians would have chosen a safe topic, something within their established expertise. Riemann chose prime numbers. He had never published on number theory before. His known work was in complex analysis and geometry. But Riemann had been thinking about primes. Privately, in his notebooks, in calculations that have only partially survived, he had been developing a new approach to an ancient question. An approach that used the tools of complex analysis, the very tools he had built his career on, to attack the problem of how primes distribute themselves among the integers. The result was über die Anzahl der Primzahlen unter einer gegebenen Größe, delivered to the Berlin Academy in November of 1859 and published in the Monatsberichte, pages 671 through 680. 8 pages. And in those 8 pages, Riemann did not merely contribute to number theory. He transformed it. He created an entirely new way of thinking about primes, a way that replaced counting and estimation with the deep structural analysis of a complex valued function. 5 years after his habilitation lecture replaced Euclidean geometry with Riemannian manifolds, he replaced classical number theory with analytic number theory. 2 fields, 2 revolutions, 1 man. In 15 years of working life, interrupted by chronic illness and ended by tuberculosis, at 39, the question that had haunted number theorists since antiquity was deceptively simple. What is the pattern in the prime numbers? Prime numbers are the most basic objects in mathematics. You know what they are. A prime is a number greater than 1 that is divisible only by 1 and itself. 2, 3, 5, 7, 11, 13, and so on. Every other whole number can be broken down into primes. 12 is 2 times 2 times 3. 100 is 2 times 2 times 5 times 5. This is called the fundamental theorem of arithmetic, and it means that prime numbers are to mathematics what atoms are to chemistry. They are the irreducible building blocks from which every whole number is constructed. If you understand the primes, you understand the integers. If you understand the integers, you have the foundation for everything else. And here is the problem that has driven mathematicians to obsession and occasionally to madness for over 2,000 years. The primes do not follow an obvious pattern. Look at the sequence. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31. There are gaps of 1, gaps of 2, gaps of 4, gaps of 6. Sometimes primes cluster together like 11 and 13. Sometimes they vanish for long stretches. If you zoom out and look at the primes up to 1 million, or 10 million, or 1 billion, they thin out. They become rarer, but they never stop. Euclid proved around 300 BCE that there are infinitely many primes, and that proof, which fits in a single paragraph, is one of the most elegant arguments in all of mathematics. There will always be another prime. The question is where? By the late 1700s, a teenage Carl Friedrich Gauss had begun to notice something in the distribution of primes. Gauss, who many consider the greatest mathematician in history, spent years compiling tables of primes by hand, and he noticed that even though the primes seemed random up close, when you zoomed out far enough, they followed a curve. Specifically, the number of primes less than some large number x was approximately x divided by the natural logarithm of x. Not exactly, but approximately, and the approximation got better the larger x became. This was an empirical observation. Gauss did not prove it. He simply noticed it in the data, the way you might notice that a seemingly random scatter of stars resolves into a spiral arm when you step back far enough. The primes looked chaotic up close. From a distance, something was steering them. But the tool that would crack this open did not come from number theory. It came from analysis, the mathematics of continuous functions, infinite sums, and convergence, and it came from Leonhard Euler. In 1737, Euler discovered something that still takes my breath away when I think about the economy of it. He showed that the sum of 1 over n to the power of s taken over all positive integers n is exactly equal to a product taken over all prime numbers p, each factor being 1 over the quantity 1 minus p to the negative s. This is called the Euler product formula. Written out, it says that the zeta function, this infinite sum over all integers, is secretly a product over only the primes. The integers and the primes are not separate subjects. They are two faces of the same function. And that function, the zeta function, is the bridge between them. I need to pause here because this is the hinge on which the entire story turns, and I want to make sure the weight of it registers. What Euler found is that there exists a single mathematical object, a function you can write down and evaluate. That encodes the relationship between the smooth, continuous world of analysis and the jagged, discrete world of prime numbers. The zeta function lives in both worlds simultaneously. It is an infinite sum that converges to a smooth function, and it is also, simultaneously, a product over every prime that exists. It is the Rosetta Stone of mathematics, and for 122 years after Euler, nobody knew how to fully exploit it. That is, until Riemann. What Riemann did in those 8 pages was something so audacious that I still think mathematicians understated when they tried to explain it to the public. The zeta function, as Euler defined it, only makes sense when the input s is a real number greater than 1. Below that, the infinite sum diverges. It blows up to infinity and stops giving meaningful answers. But Riemann was not working with real numbers. He was working with complex numbers, numbers with 2 components, a real part and an imaginary part, numbers that live on a plane. And he showed that the zeta function could be extended, analytically continued, to a function defined on the entire complex plane, with just one exception, at the point s equals 1, where it has a pole, a point where the function shoots off to infinity. This extension is not a cheat. It is not redefining the function or making up new values. Analytic continuation is a rigorous technique in complex analysis where the properties of a function in one region uniquely determine its values everywhere else. Think of it this way. If you know the shape of a piece of a holographic plate, you can reconstruct the entire image. The piece contains enough information to determine the whole. Analytic functions work the same way. If you know the function's values in one region, the mathematical rules of complex analysis force the function's values everywhere else. There is no choice involved. There is no ambiguity. There is only one way to extend the zeta function to the full complex plane. And Riemann found it. And what he found when he did this was remarkable. The extended zeta function was not just a technical convenience. It had properties that the original sum could never have revealed. Riemann derived a functional equation, a symmetry relating zeta of s to zeta of 1 minus s, showing that the function has a deep bilateral symmetry around the vertical line at real part, 1/2. He then wrote down what we now call the Riemann Xi function, a modified version of zeta that strips away the pole at s equals 1 and the gamma function factors, leaving a function that is symmetric, entire, and has exactly the same zeros as the non-trivial zeros of the original zeta function. And he wrote down an expression for the number of zeros up to a given height. the formula now named after him and von Mangold. All of this was in the 8 pages. 8 pages. Riemann did not just conjecture the hypothesis that bears his name. He built the entire framework for studying it, the analytic continuation, the functional equation, the connection to the prime counting function, the explicit formula relating primes to zeros, and the conjecture itself. Any one of these results would have been a major contribution to mathematics. Together, in 8 pages, they constitute one of the most concentrated bursts of mathematical genius in recorded history. And at the critical moment, when Riemann stated his conjecture about the location of the zeros, he wrote 4 words in German that translate roughly as, "It is very probable," sehr wahrscheinlich. He saw it. He did not prove it. He moved on, as if the most important unsolved problem in mathematics was a parenthetical observation on the way to something else. And when Riemann extended the zeta function to the full complex plane, the function revealed a hidden architecture that nobody had seen before. It had zeros, points where the function equals exactly 0. Some of these were obvious, predictable. The zeta function equals 0 at every negative even integer, -2, -4, -6, and so on. These are called the trivial zeros, and they come from the symmetry of the function, specifically from a factor involving the sine function that appears in the functional equation Riemann derived connecting zeta of s to zeta of 1 minus s. They are interesting, but not mysterious. But then there were the other zeros, the non-trivial zeros, the ones that live inside a vertical strip of the complex plane called the critical strip, the region where the real part of S is between 0 and 1. These zeros do not follow from any simple symmetry. They are not predictable from any known formula, and there are infinitely many of them, climbing up the complex plane at heights that increase roughly logarithmically, according to the Riemann von Mangold formula, which says the number of zeros with imaginary part less than t is approximately t over 2 pi times the natural logarithm of t over 2 pi. Now here is what Riemann discovered, and here is why those 8 pages changed mathematics forever. Each non-trivial zero of the zeta function corresponds to a wave, a specific oscillation with a specific frequency. And when you add up all of those waves, when you superimpose them, the result is the distribution of prime numbers. The primes are not random. They are the sum of infinitely many waves, each one dictated by a zero of the zeta function. The explicit formula that Riemann wrote down, later made rigorous by Hans von Mangold in 1895, says that the prime counting function, the function that tells you how many primes exist below any given number, equals a smooth main term minus a sum over every non-trivial zero, plus some smaller correction terms. Every zero contributes an oscillation. Every oscillation has an amplitude determined by the real part of the zero, and a frequency determined by its imaginary part. This is what mathematicians mean when they call the zeros of the zeta function the music of the primes. It is not a metaphor. It is a precise mathematical statement. The primes are the harmony produced by the superposition of infinitely many tones, and each tone is a zero of the Riemann zeta function. Marcus du Sautoy, the Simonyi Professor of Public Understanding of Science at Oxford, has used exactly this language, and it is as close to literal as mathematics gets. And here is where the Riemann hypothesis enters. And here is where the ground starts to give way beneath your feet. The amplitude of each wave in the explicit formula is determined by the real part of the corresponding zero. If a zero has real part exactly 1/2, its contribution to the prime counting function is as small as possible. It oscillates, but with an amplitude proportional to the square root of x. If even one zero had a real part greater than 1/2, its contribution would be larger. The oscillation would be bigger. The primes would deviate from their expected smooth distribution by more than the square root of x. The error term in the prime number theorem would be worse than it should be. In 1901, Helgi von Koch proved that the Riemann hypothesis is exactly equivalent to saying the error in the prime number theorem is of order x to the 1/2 times the logarithm of x, and no worse. If RH is true, the primes are as orderly as they can possibly be. If RH is false, there is a hidden chaos in the primes that we have never detected. The Riemann hypothesis says that every single non-trivial zero of the zeta function has real part exactly equal to 1/2. All of them, all infinitely many of them, lie on a single vertical line in the complex plane. The critical line, real part 1/2, no exceptions, no deviations, across infinity. That is what those 8 pages conjecture. That is what nobody has proved. And the precision required to state it is matched by the precision with which it has been verified. The first non-trivial zero has imaginary part 14.134725, and its real part is exactly 1/2. The second has imaginary part 21.022040, also exactly on the line. The third is at 25.01. 0858. On the line, the 100th zero, the 1000th, the millionth, the billionth, all on the line. As of 2021, David Platt and Tim Trudgian, in a paper published in the Bulletin of the London Mathematical Society, volume 53, pages 792 through 797, verified using rigorous interval arithmetic that every non-trivial zero with imaginary part up to 3.00001753328 times 10 to the 12th is on the critical line. That is more than 3 trillion zeros, every single one exactly where Riemann said they would be. And yet, nobody can prove the 3 trillion and first zero will be there. Nobody can prove the next one will be there either, or the next billion. The gap between overwhelming evidence and mathematical proof has not closed in 167 years. And there is a reason for that, a reason that mathematicians do not talk about publicly very often. And it is not that the problem is merely hard in the way that building a rocket to Mars is hard, where you just need more engineering and more time. The Riemann hypothesis resists proof in a way that suggests something deeper is going on, something about the limits of the methods humans currently possess, possibly something about the limits of the methods humans can ever possess. But I am getting ahead of myself. Before we go there, you need to see how badly the best mathematical minds in history have failed against these 8 pages, because the story of the attempts to prove the Riemann hypothesis is not a story of steady progress. It is a story of brilliant people running at a wall over and over for 167 years, and the wall not moving. And I want to make sure the weight of the explicit formula actually lands, because when most people encounter this idea, they treat it as a mathematical abstraction. It is not. Let me give you an analogy that I think makes it visceral. Imagine you are standing in a concert hall. The orchestra is playing a piece of music. You can hear the music perfectly, but you cannot see the orchestra. You cannot see the instruments. All you have is the sound. Now imagine that a mathematician walks up to you and says that every note you are hearing, every chord, every harmony, every dissonance, every pattern in the music is determined by the resonant frequencies of the instruments. If you knew where every instrument was tuned, you would know the entire piece. That is the relationship between the zeros of the zeta function and the primes. The primes are the music. The zeros are the frequencies. And the Riemann hypothesis says every instrument is tuned to the same fundamental pitch. Every zero sits at real part 1/2. Every frequency contributes at the same amplitude. The music of the primes is an orchestra where every instrument plays at the same volume. And the result, the interference pattern produced by all those equal amplitude waves, is the distribution of prime numbers that Gauss noticed as a teenager counting by hand at his desk. But if even one instrument were tuned differently, if even one zero sat at a real part greater than 1/2, it would play louder than the others. Its wave would dominate. The distribution of primes would develop a bulge, a deviation, a hidden disorder that would manifest at some unimaginably large scale. We have checked 3 trillion instruments, and they are all in tune. But we cannot prove the next one will be. And we cannot even estimate where a single out-of-tune instrument might appear, because the concert hall is infinite. The orchestra has infinitely many instruments, and the piece never ends. And here is a detail that gives the scale of what has been checked a more precise shape. 3 trillion zeros means 3 times 10 to the 12th. If you tried to count to 3 trillion at one number per second, without sleeping, without pausing, it would take you roughly 95,000 years. That is about 15 times longer than all of recorded human civilization. Platt and Trudgian verified every single zero up to that height, using rigorous interval arithmetic that leaves no room for rounding error. Every one had its real part exactly equal to 1/2, not one deviated. But there is a reason why even 3 trillion should not make you comfortable. There is a well-known example in number theory where overwhelming computational evidence turned out to be misleading. The skews number concerns a comparison between the prime counting function pi of x and the logarithmic integral LE of x. For every value of x that anyone had ever computed, pi of x was less than LE of x, always, without exception. But in 1914, Littlewood proved that the inequality reverses infinitely often, and the first reversal happens at a number so large, roughly 10 to the 316, according to the original skews bound, that no direct computation could reach it in the lifetime of any conceivable computer. The evidence was overwhelming. Every case checked was consistent, and the general claim was wrong. 3 trillion is a very large number. Infinity is larger. I am not suggesting the Riemann hypothesis is false. The depth of the evidence, the random matrix connection, the spectral interpretation, the narrowing of the de Bruijn-Newman constant, everything points overwhelmingly toward truth. I am suggesting that the gap between evidence and proof, in a domain where even 3 trillion verified cases can be compatible with eventual failure, is not a technicality. It is the central mystery of this entire story. And I want to make the stakes of this concrete because it is easy to treat the Riemann hypothesis as an abstract problem about abstract objects. It is not. Consider prime gaps. The gap between consecutive primes. Between 2 and 3, the gap is 1. Between 3 and 5, the gap is 2. Between 7 and 11, the gap is 4. Between 23 and 29, the gap is 6. As numbers get larger, the gaps get wider on average. Around 1 million, the average gap between consecutive primes is about 14. Around 1 billion, it is about 21. Around 1 trillion, about 27. The primes thin out logarithmically, exactly as Gauss predicted. But the actual gaps fluctuate. Sometimes primes cluster together even in regions where they are sparse. Twin primes like 1 billion 49 and 1 billion 51, or however the specific examples fall. Sometimes the gaps are anomalously large, and the Riemann hypothesis constrains how wild those fluctuations can be. If RH is true, the error in the prime counting function grows no faster than roughly the square root of x times the logarithm of x. This means the primes cannot deviate too far from their expected positions. There cannot be unexpectedly huge gaps or unexpectedly dense clusters beyond a certain quantifiable bound. If RH is false, the error could be larger, the primes could be wilder than we think. There could be hidden pockets of chaos in the distribution of primes at scales so large no computation has reached them, and perhaps no computation ever will. The Riemann hypothesis is not an abstract constraint on an abstract function. It is a guarantee that the most fundamental objects in mathematics, the objects your phone uses to encrypt your messages, behave in an orderly way, and that guarantee is unproved. The first real progress on Riemann's conjecture did not come until 37 years after his death. In 1896, two mathematicians working independently, Jacques Hadamard in France and Charles-Jean de la Vallée-Poussin in Belgium, proved the prime number theorem. This was the result Gauss had conjectured as a teenager from his tables. The number of primes less than some number x is asymptotically equal to the logarithmic integral, LE of x. The primes thin out exactly the way Gauss predicted. But here is what matters for our story. Both Hadamard and de la Vallée-Poussin proved this theorem by studying the Riemann zeta function. Specifically, they proved that the zeta function has no zeros on the vertical line where the real part of s equals 1, not the critical line at 1/2, the line at 1. They proved a much weaker result than Riemann had conjectured, and even that weaker result was enough to establish the prime number theorem, one of the landmark results of 19th century mathematics. The Riemann hypothesis says that not only are there no zeros on the line at 1, there are no zeros anywhere in the critical strip except on the line at 1/2. The distance between what Hadamard and de la Vallée-Poussin proved and what Riemann conjectured is the distance between there are no criminals on this particular street and there are no criminals anywhere in the entire city. And that distance has been the battleground for every mathematician who has tried to prove RH since. 4 years later, David Hilbert stood before the International Congress of Mathematicians in Paris on the 8th of August, 1900, and delivered the most famous address in the history of mathematics. He presented a list of 23 unsolved problems that he believed would shape the direction of mathematics in the 20th century. The Riemann hypothesis was number 8. Hilbert is widely quoted as having said, "If I were to awaken after having slept for 1,000 years, my first question would be, has the Riemann hypothesis been proven?" I want to be honest with you about this quote. The earliest traceable source is Richard Bellman's 1961 book, A Brief Introduction to Theta Functions, page 34, where it is attributed to Hilbert without a specific occasion. No original German text has ever surfaced. Some versions give 500 years instead of 1,000. The quote may be apocryphal, but it captures something real about the stature of this problem in mathematics. Hilbert's authentic epitaph, the one carved on his tombstone in Göttingen, reads, "Wir müssen wissen, wir werden wissen. We must know, we will know." He said those words in a radio address in 1930, one day after Gödel presented the incompleteness theorems in Königsberg, theorems which showed that Hilbert's motto was, at a fundamental level, wrong. There are things we must know that we may never know, and the Riemann hypothesis might be one of them. But I am getting ahead of the story. The first person to make real progress on the zeros themselves was a man whose personality could not have been more different from the shy, gentle Riemann. Godfrey Harold Hardy was a Cambridge mathematician, born in 1877, who cultivated eccentricity the way other people cultivate gardens. He was an avowed atheist in an era when that carried real social cost. He played cricket obsessively and organized his life around the sports calendar. He had a famous and unshakable aversion to mirrors and photographs, reportedly covering mirrors in hotel rooms upon arrival. He had a creative partnership with John Edison Littlewood that lasted 35 years and produced over 100 joint papers, a collaboration so prolific and so deeply intertwined that some continental mathematicians joked that Littlewood did not actually exist and was merely a pen name Hardy used for his best work. And he had, by his own admission, an obsession with the Riemann hypothesis that bordered on the spiritual. In his 1940 memoir, A Mathematician's Apology, Hardy described the problem as the most important unsolved question in mathematics. He carried a list of goals with him. At the top, famously, was prove the Riemann hypothesis. Below that, make 211, not out in the fourth innings of the last test match at the Oval. Hardy was not a man who ranked trivial things alongside serious ones. Cricket was deadly serious to Hardy, and the Riemann hypothesis was more serious still. Hardy had another relationship that matters to this story, though it touches the Riemann hypothesis only tangentially. In 1913, he received a letter from Srinivasa Ramanujan, a self-taught Indian mathematician working as a clerk in Madras. The letter contained results so extraordinary that Hardy initially suspected it was a hoax. He showed it to Littlewood. Together, they concluded that the results could only have been produced by a mathematician of the first rank, someone who had independently discovered and rediscovered vast tracts of mathematics that the European tradition had taken centuries to develop. Hardy brought Ramanujan to Cambridge. Their collaboration, which lasted until Ramanujan's return to India in 1919 and his death in 1920 at the age of 32, is one of the most famous in the history of mathematics. Ramanujan's notebooks, published posthumously and still being mined for new results a century later, contain formulas for the partition function, for infinite series, for continued fractions, and for modular forms that nobody at the time knew how to prove, and that some mathematicians still find mysterious. Why does Ramanujan matter to this story? Because Ramanujan worked extensively with the Zeta function and with closely related functions. Some of his formulas are connected to the distribution of primes, and Hardy once said that his discovery of Ramanujan was the one romantic incident of his life. Hardy, who spent decades on the Riemann hypothesis, who carried it as an obsession, who mailed postcards about it to defeat God, also carried the memory of a young man from India who saw mathematical structures that nobody else could see and who died at 32. The parallel to Riemann, who saw structures nobody else could see and died at 39, is not something Hardy would have missed. Hardy himself died in 1947 at the age of 70. He had attempted suicide 2 years earlier. His final years were marked by declining health and a growing sense that his best mathematical work was behind him. The Riemann hypothesis was not proved in his lifetime. He had worked on it for over 30 years. In 1914, Hardy proved the first major result about the zeros in a paper published in the Comptes Rendus de l'Académie des Sciences in Paris, volume 158. Pages 1012 through 1014, he showed that infinitely many non-trivial zeros of the Riemann zeta function lie on the critical line. This was not the Riemann hypothesis. Not close. It said that the critical line was not empty. There were infinitely many zeros on it, but it said nothing about whether there might also be infinitely many zeros off it. Edmund Landau, one of the leading number theorists of the era, called Hardy's result one of the most significant advances in mathematics of recent times. Even a partial result about the zeros was enough to rattle the mathematical world. There is a story about Hardy that I want to tell here because it reveals something about the psychological relationship between mathematicians and this problem. Hardy was terrified of sea travel. On one occasion, after visiting his friend and fellow mathematician Harald Bohr in Denmark, Hardy mailed a postcard from the dock before boarding the ferry across the North Sea. The postcard read, "I have proved the Riemann hypothesis." His reasoning was theological, or rather anti-theological. Hardy believed that God, if God existed, would not allow him to die at sea in a state of undeserved mathematical glory. The postcard was life insurance. If the ferry sank, the mathematical community would spend years searching for a proof that did not exist. And God, being spiteful but not careless, would never permit such unearned fame. So the ferry would not sink. Hardy survived the crossing. The Riemann hypothesis remained unproved. The story is usually told as a joke. I think it is actually a window into what this problem does to the people who work on it. It becomes a companion, an obsession, something you carry and think about when you should be thinking about the sea. Hardy and Littlewood pushed further in 1921, proving that the number of zeros on the critical line up to height t grows at least linearly with t. Good, but still a lower bound. The Riemann hypothesis demands all zeros, not just a lot of them. Then in 1942, Atle Selberg proved something stronger. Selberg was Norwegian, born in 1917, and he was as reserved and meticulous as Hardy was flamboyant. He spent most of his career at the Institute for Advanced Study in Princeton, where he became known for producing deep results with a minimum of machinery, proving things with elegant simplicity where others had used heavy technology. Selberg showed that a positive proportion of the non-trivial zeros lie on the critical line, not just infinitely many, a positive proportion, meaning the fraction of zeros on the line did not shrink to zero as you looked higher and higher. It stayed bounded away from zero. Selberg would win the Fields Medal in 1950, but the years around that award were complicated by one of the ugliest priority disputes in 20th century mathematics. In 1948, Selberg discovered a new asymptotic formula, now called the Selberg fundamental formula, that related the prime counting function to certain weighted sums involving primes. The formula did not itself prove the prime number theorem, but it was a critical new ingredient. Selberg showed his formula to Paul Erdos, the Hungarian-born itinerant mathematician, who is famous for having published more papers than any mathematician in history, over 1,500, and for living out of a suitcase, traveling from university to university, collaborating with everyone. Erdos took Selberg's formula and, working from it, found an elementary derivation of a key step that brought the elementary proof of the prime number theorem within reach. Elementary here does not mean easy. It means without the use of complex analysis, without the Zeta function, without analytic continuation, a proof using only real analysis and arithmetic, the kind of proof that Hadamard and de la Vallée-Poussin had not been able to find and that many mathematicians believed did not exist. What happened next depends on who you ask. Selberg believed the fundamental formula was the core insight and that the elementary proof was primarily his achievement. Erdos believed he had contributed an essential step and that the proof should be published jointly. They could not agree. Selberg published his proof alone. Erdos published his own version separately. The mathematical community split. Some sided with Selberg, some sided with Erdos. Ernst Strauss, a former assistant to Einstein, tried to mediate and failed. The dispute permanently damaged the relationship between Selberg and Erdos, two of the greatest mathematicians of the 20th century, and it cast a shadow over the Fields Medal that Selberg received partly for this work. The irony is painful. The prime number theorem, a result about the distribution of the primes, a result that depends on the behavior of the zeta function, a result connected at its deepest level to the Riemann hypothesis, was proved elementarily for the first time in the same decade that two of its provers were unable to resolve a dispute about credit. The primes, indifferent to human vanity, continued falling where they always had. The humans who studied them were less orderly. The next leap came from Norman Levinson at MIT in 1974. Levinson proved that at least 1/3 of the non-trivial zeros lie on the critical line. 1/3. After 115 years, mathematicians could prove that at least 33% of the zeros were where Riemann said all of them should be. Levinson's proof was technically brilliant, using a method that linked the zeros of the zeta function to the zeros of its derivative. In a follow-up paper the next year, he pushed the figure to 34.74%. Levinson was diagnosed with a brain tumor around this time and died in 1975. He never saw his record broken. But it was broken. In 1989, J. Brian Conry, now the director of the American Institute of Mathematics, proved that more than 40% of the non-trivial zeros lie on the critical line. Specifically, more than 40.77%. This was a significant jump over Levinson's result, requiring new ideas about the behavior of the zeta function and its modifications. It remains the most widely cited headline figure. Since then, the record has crept upward. In 2012, Xiaoji Feng pushed it to 41.28% in a paper in the Journal of Number Theory. And in 2020, Kyle Pratt, Nathan Robles, Alexandru Zaharescu, and Dirk Zeindler improved the bound to 41.72%, the current record. Let me put that trajectory in perspective. In 1914, Hardy proved infinitely many zeros are on the line, but could not quantify the proportion. In 1942, Selberg proved a positive proportion, but could not specify how large. In 1974, Levinson proved at least 1/3. In 1989, Conry proved at least 2/5. In 2020, the record stands at about 42%. After 167 years of sustained effort by some of the most powerful mathematical minds who have ever lived, we can prove that roughly 42% of the zeros are where all of them should be. The improvement has been real, but the distance to 100% is not shrinking in a way that suggests arrival is near. Each increment has required new ideas, new techniques, new frameworks, and each increment has been smaller than the last. The curve of progress is flattening, not steepening. And on the computational side, the story is similar in its mixture of triumph and frustration. Alan Turing, the same Alan Turing who broke the Enigma code at Bletchley Park, laid the theoretical foundations of computer science and proposed the Turing test for machine intelligence, was also deeply interested in the Riemann hypothesis. Turing developed a new method for rigorously verifying that all zeros in a given range of the critical line are accounted for and lie on the line. His paper, published posthumously in 1953 in the Proceedings of the London Mathematical Society, Series 3, Volume 3, pages 99 through 117, introduced what is now called Turing's method. He ran it on the Manchester Mark I, one of the earliest electronic stored program computers, checking zeros in specific intervals around the 1400th zero and near the 20,000th, he found no counterexample. I want to pause on Turing for a moment, because his story matters to this narrative, for reasons beyond mathematics. Turing was convicted of gross indecency in 1952 for his homosexuality, was subjected to chemical castration as a condition of his sentence, and died on the 7th of June, 1954, from cyanide poisoning, in circumstances that remain officially classified as suicide, though some have argued it may have been accidental. He was 41 years old. The establishment that had benefited from his wartime code-breaking, that owed him a debt that cannot be quantified in terms of lives saved and wars shortened, prosecuted him for who he was. He spent some of the last years of his life developing methods to check the Riemann zeros, and the method he invented is still the standard technique used by every large-scale computation 70 years later. The zeros he checked are still on the line. The man who checked them was destroyed by the same society that used his genius. This is not tangential to the story of the Riemann hypothesis. It is part of the pattern. After Turing, the computational verification accelerated in a way that tracks the exponential growth of computing power itself. DH. Lima extended the verification to the first 25,000 zeros in 1956 using the SWAC computer at UCLA. By 1966, R.S. Lehman had checked 300,000 zeros. In 1968, Rosser, Yohe, and Schoenfeld pushed the count to 3.5 million. By 1979, Richard Brent had verified the first 81 million zeros. In 1982, Terile and van der Loon reached 300 million. By 1986, van der Loon, Terile, and Winter had verified 1.5 billion zeros. Each computation was more extensive than the last. Each used more powerful hardware and more refined algorithms. Each confirmed that every zero lay exactly on the critical line, and each, despite its vastness, covered only an infinitesimal fraction of the infinitely many zeros that exist. The numbers have a relentless quality. 70,000 zeros verified by 1958, 1 million by the mid-60s, 100 million by the late 70s, 1 billion by the mid-80s, 10 billion by the early 2000s. Sebastian Wodeniski's Zeta Grid distributed computing project claimed 100 billion zeros in 2004, though this was not published in a peer-reviewed journal and is not considered rigorous by the standards of mathematical proof. Xavier Gordon, using the Odlyzko-Schoenhag algorithm, announced 10 trillion zeros in 2004 with more rigor, and then Platt and Trudgian's 2021 result, published in the Bulletin of the London Mathematical Society, established the current record of 3 trillion rigorously verified zeros using interval arithmetic that leaves no room for rounding error or numerical instability. Every single zero on the line, no exceptions. And then Andrew Odlyzko did something that transformed the field from counting into insight. He did not just verify zeros at the bottom of the critical line, where everyone else was checking. He went high, astronomically high. He computed zeros near the 10 to the 20th zero, the 10 to the 21st, the 10 to the 22nd. At those heights, the zeros are packed so densely that the gaps between consecutive zeros are measured in thousandths and 10,000ths of a unit. The statistical pattern of those gaps, the pair correlation, can be measured with extreme precision at those heights because you have so many nearby zeros to analyze. Odlyzko published his results in a series of papers and technical reports through the 80s and 90s, including a landmark paper titled The 10 to the 20th Zero of the Riemann Zeta Function, and 175 million of its neighbors. The title alone conveys the scale. He did not just compute 1 0 at that height. He computed 175 million consecutive zeros in a neighborhood near the 10 to the 20th zero. And he compared their spacing statistics to the predictions of random matrix theory. The result is best conveyed visually. If you plot the distribution of normalized spacings between consecutive zeros of the zeta function on one graph, and the distribution of normalized spacings between eigenvalues of random Hermitian matrices from the Gaussian unitary ensemble on another graph, you cannot tell them apart. The curves overlay each other with a precision that leaves no room for doubt. Odlyzko's plots, which have been reproduced in countless textbooks and survey articles since, show two distributions that are indistinguishable at the resolution of the data. The zeros of the zeta function at height 10 to the 20 behave statistically identically to the eigenvalues of random matrices used to model nuclear spectra. And at height 10 to the 22, the match is even more precise because the sample size is larger and the statistics are tighter. What Odlyzko found was not merely a confirmation of Montgomery's theoretical formula. It was empirical proof that the connection between number theory and quantum physics is not an artifact of a particular approximation or a particular range. It persists at extraordinary heights. It persists as the zeros get denser. It persists as far as anyone has ever been able to compute, and it changed the way mathematicians think about this problem. After Odlyzko, the Riemann hypothesis was no longer just a conjecture about a number-theoretic function. It was the keystone of a bridge between mathematics and physics that nobody had expected and nobody could explain. Because in 1972, something happened in a tea room at the Institute for Advanced Study that would change the way we think about this connection forever. Hugh Montgomery was 28 years old. He was a number theorist at the University of Michigan who had been studying the pair correlation of the non-trivial zeros of the zeta function. Pair correlation is exactly what it sounds like. You take the zeros, you look at the spacing between nearby pairs, and you study the statistical distribution of those gaps. Are the gaps random? Are they clustered? Is there a pattern in how close together the zeros like to be? Montgomery had derived a formula for this distribution. It was a specific mathematical expression involving sine functions, and he believed it described how the zeros of the zeta function spaced themselves out. He had come to the Institute for Advanced Study to show his result to Alain Selberg, who was the world's foremost authority on the zeta function's zeros. During afternoon tea at the Institute, an event that happened daily, and served as the informal networking hub of mathematical Princeton, Sarvadaman Chawla, an Indian-born number theorist, introduced Montgomery to Freeman Dyson. Dyson was a British theoretical physicist, then about 70, who had spent most of his career studying quantum mechanical systems. His particular expertise was in the statistical properties of the energy levels of heavy atomic nuclei. What happened next is one of those moments in the history of ideas that feels almost scripted in its perfection. Montgomery described his pair correlation formula to Dyson, and Dyson, without a moment's hesitation, told Montgomery that his formula was the pair correlation function for the eigenvalues of large random Hermitian matrices in the Gaussian unitary ensemble. I need to be very careful here, because the significance of this moment is easy to understate. Montgomery had derived a formula from pure mathematics, from the internal structure of the zeta function zeros, from number theory. Dyson recognized it instantly as a formula from nuclear physics, from the behavior of quantum energy levels in complex atomic nuclei. These are not related subjects. Number theory studies the properties of integers. nuclear physics studies the behavior of subatomic particles in heavy atoms. The mathematical tools are different. The physical intuitions are different. The histories are different. The communities of researchers barely overlap. And the pair correlation formula was the same. 1 minus the quantity sine of pi u over pi u, all squared. That is the formula. Montgomery derived it from the Zeta function. Dyson recognized it from nuclear spectra, the same formula, in two completely different fields, governing two completely different sets of objects. The zeros of a function that encodes the distribution of prime numbers, and the energy levels of uranium nuclei. The meeting happened on the 6th of April, 1972. It has been documented by multiple participants, retold consistently for over 50 years, and is universally regarded as one of the most important accidental discoveries in the history of mathematics. Montgomery himself has described it in numerous interviews and lectures, and it opened a door that has not been closed since. Because Odlyzko's computations in the 1980s confirmed it. When Odlyzko computed the pair correlation of zeros at heights around the 10 to the 20th zero and compared it to the random matrix prediction, the agreement was not approximate. It was not suggestive. It was exact to every decimal place he could measure. The zeros of the Riemann Zeta function and the eigenvalues of large random Hermitian matrices follow the same statistics. Not roughly, not to first order, to every order of precision available. This is now called the Montgomery-Odlyzko law, and its implications go far beyond the Riemann hypothesis itself, though the Riemann hypothesis sits at its center. Because if the zeros are not on the critical line, if even one zero deviates from real part 1/2, then the random matrix match breaks down. The GUI statistics assume a specific symmetry in the zeros, exactly the symmetry that the Riemann hypothesis guarantees. The connection between prime numbers and nuclear physics requires the Riemann hypothesis to be true. I want you to sit with that for a moment. Prime numbers were studied by Euclid around 300 BCE. Random matrix theory was developed by Eugene Wigner in the 1950s to describe nuclear spectra. These two subjects were developed by different people, in different centuries, for different purposes, using entirely different methods, and they produce the same statistics. The building blocks of arithmetic obey the same laws as the energy levels of atomic nuclei. A function written down in 1859 by a man who had never heard of an atomic nucleus, who had no concept of quantum mechanics, who could not have imagined that atoms had internal structure. That function describes the same statistical pattern as the spectrum of a quantum system that would not be discovered for almost a century. This is not a coincidence in any meaningful sense of the word. It is too precise, too extensive, too deeply embedded in the structure of both subjects to be accidental. Something is connecting these two domains of reality. Some structure underlies both prime numbers and quantum systems, and the Riemann hypothesis is, in some sense, that nobody has been able to make fully precise the statement that this connection exists and is exact. The idea that was already in the air before Montgomery met Dyson, the idea that gave this connection its theoretical framework, is the Hilbert-Polya conjecture. Sometime around 1912 to 1914, the Hungarian mathematician George Polya was visiting Göttingen and had a conversation with Edmund Landau. Landau asked Polya if he could think of a physical reason why the Riemann hypothesis should be true. Polya's response, recalled in a letter he wrote to Andrew Odlyzko on the 3rd of January 1982, was this: if the imaginary parts of the non-trivial zeros of the zeta function are the eigenvalues of some self-adjoint operator on a Hilbert space, then they would automatically be real numbers and the zeros would automatically lie on the critical line because the eigenvalues of a self-adjoint operator are always real. That is the spectral theorem, one of the most fundamental results in functional analysis. If such an operator existed, the Riemann hypothesis would be a trivial consequence. David Hilbert independently arrived at a similar idea, and the conjecture now bears both their names. The Hilbert-Polya conjecture says there exists a self-adjoint operator whose eigenvalues are exactly the imaginary parts of the non-trivial zeros of the zeta function. Find the operator, prove it is self-adjoint, and the Riemann hypothesis falls out automatically. The conjecture has been floating around mathematics for over a century, and the Montgomery-Dyson connection gave it teeth, because if the zeros have GUE statistics, then they genuinely are behaving like eigenvalues of a quantum Hamiltonian. The operator is not just a theoretical fantasy. The data says it should exist. In the late 1990s, Michael Berry and Jonathan Keating at the University of Bristol proposed a specific candidate. In their paper, H equals XP and the Riemann zeros, published in the plenum volume Supersymmetry and Trace Formulae, Chaos and Disorder in 1999, and in a companion paper, The Riemann Zeros and Eigenvalue Asymptotics in SEAM Review, Volume 41, Number 2. They argued that the relevant operator should arise from quantizing the classical Hamiltonian H equals XP, where x is position and p is momentum. This is an unusual Hamiltonian. In classical mechanics, it generates exponential dilation, not oscillation. But Berry and Keating showed that under appropriate boundary conditions, the quantized version should have a discrete spectrum, and that spectrum should match the Riemann zeros. The Berry-Keating proposal was beautiful. It was physically motivated. It connected the Riemann hypothesis to quantum chaos, the study of quantum systems whose classical counterparts are chaotic. And it was incomplete. Proving rigorously that the quantized H equals XP operator has the right eigenvalues has remained beyond reach. The proposal is a signpost, not a proof. And then there is Alain Connes. Connes is a French mathematician who won the Fields Medal in 1982 for his work on operator algebras and von Neumann algebras. Since the late 1990s, he has pursued what may be the most ambitious approach to the Riemann hypothesis ever attempted. His approach uses non-commutative geometry, a framework he largely invented, which extends geometric ideas to spaces that do not commute, spaces where the order in which you perform operations matters. In a paper titled Trace Formula in Non-Commutative Geometry and the Zeros of the Riemann Zeta Function, published in Selecta Mathematica, New Series, Volume 5, Number 1, in 1999, and available on the arXiv as Math 9811068, Connes gave a spectral interpretation of the critical zeros of the zeta function as an absorption spectrum, not an emission spectrum, where you see bright lines, but an absorption spectrum, where you see dark lines against a background. The zeros appear as missing frequencies in a certain trace formula defined on the Adel class space, a specific mathematical space constructed from the Adels, which are a way of packaging all the different prime number perspectives on arithmetic into a single object. His abstract contains a claim that I think is extraordinary in its ambition. He writes that his framework reduces the Riemann hypothesis to the validity of the trace formula. He has not proved the trace formula in sufficient generality to settle RH, but he has shown that if a certain positivity condition holds, a condition analogous to the Weil positivity used in the proof of the Riemann hypothesis for curves over finite fields, then the Riemann hypothesis for the classical zeta function follows. Connors has continued this program with Katerina Consani over the past 2 decades, developing the arithmetic site, the scaling site, and a detailed architecture of characteristic 1 geometry. And in February of 2026, Cons posted a new survey paper to the Arxiv reference 2600 and 2.04022, titled The Riemann Hypothesis, Past, Present, and a Letter Through Time. It is structured as a letter to Riemann himself, 167 years after the original paper, and it contains a numerical experiment that I have read 3 times and still find difficult to fully absorb. Using his framework and using only the primes 2, 3, 5, 7, and 11, Connors was able to approximate the first 50 non-trivial zeros of the zeta function. The accuracies ranged from 10 to the -3 to 2.6 times 10 to the -55, all provably on the critical line. 5 primes, 50 zeros, up to 55 decimal places of accuracy. The structure is there. The zeros are being constrained by information contained in the smallest primes. The architecture Connors has built can see the zeros forming on the critical line with extraordinary precision. And still the final step, the proof that the positivity condition holds in full generality, remains open. The door is visible, the key is in the lock, and it will not turn. I think this is the place in the story where the frustration becomes palpable, where you begin to feel what working mathematicians feel about this problem, which is not just intellectual curiosity, but something closer to grief. Every approach works partially. Every framework illuminates part of the structure. Every computation confirms the conjecture to another decimal place, another trillion zeros, another percentage point of the proportion on the line, and the wall does not move. Because in between the careful incremental advances, there have been the catastrophes, the high-profile attempts that ended not in progress, but in public humiliation, personal disintegration, or both. And those stories, taken together, tell you something about the Riemann hypothesis, that the partial results and the computations do not. They tell you what the problem does to the people who try to solve it. The most haunting of these stories begins in early 1959 at Columbia University in New York. The American Mathematical Society had organized a special lecture. The speaker was John Forbes Nash Jr., 30 years old, already regarded as one of the most brilliant mathematicians of his generation. Nash had done groundbreaking work in game theory, for which he would eventually win the Nobel Prize in Economics in 1994. He had solved problems in differential geometry that experts thought were permanently out of reach. His colleagues at MIT and Princeton spoke about his mathematical ability with a kind of awe that academics rarely permit themselves. He was not merely talented, he was operating at a level that most mathematicians encounter once in a generation, if they are lucky. Nash had recently turned his attention to the Riemann hypothesis. He had told colleagues he believed he had a proof. The mathematical community, aware of his extraordinary track record, showed up to hear it. Roughly 250 mathematicians gathered in the lecture hall at Columbia. What happened next is recorded in 2 sources I trust. Sylvia Nazar's biography, A Beautiful Mind, published by Simon & Schuster in 1998, pages 253 and 254, reconstructs the event from interviews with people who were present. Carl Sabar's Dr. Riemann's Zeros, published by Atlantic Books in 2002, pages 87 and 88, provides direct quotes from Donald Newman, a mathematician who knew Nash from MIT. Nash began to present his proof, and as he went deeper into the argument, the audience realized that something was profoundly wrong. Not wrong in the way that a proof can have a subtle gap, an error in one step that might be repairable, wrong in a way that could not be repaired. The proof was not merely incorrect, it was incoherent. Newman later told Sabak, and I want to give you his exact words because paraphrase would not do them justice. One word did not fit with the other. Everyone knew something was wrong. It was not his math, it was his chatter. The math was just lunatic. The audience knew what they were watching. Many of them understood it before Nash did. They were watching a brilliant mind come apart in real time. Nash had developed schizophrenia, and the Columbia lecture was one of the first occasions when it became unmistakably, publicly apparent. He was committed to McLean Hospital in April of 1959. He would spend the next several decades in and out of psychiatric institutions, unable to distinguish his mathematical insights from his delusions, the two having become entangled in a way that nobody, including Nash himself, could separate. I need you to understand the weight of this in the context of the Riemann hypothesis. Nash was not a crank. He was not a well-meaning amateur. He was one of the most powerful mathematical minds of the 20th century. His work on Nash equilibrium reshaped economics. His embedding theorems in Riemannian geometry were described by Mikhail Gromov, one of the greatest geometers alive, as something only a genius with no regard for the conventional wisdom could have achieved. And the Riemann hypothesis broke him, not because the mathematics defeated him, though it almost certainly would have defeated him. In any case, because his attempt to reach the answer took him into mental territory from which it required decades to return. The problem did not simply resist. It consumed. Nash eventually recovered sufficiently to return to mathematics, shared the Nobel Prize with John Harsanyi and Reinhard Selten in 1994, and won the Abel Prize in 2015. He and his wife Alicia died in a taxi accident on the New Jersey Turnpike on the 23rd of May, 2015, returning from the Abel Prize ceremony in Norway. He was 86. The Riemann hypothesis, the problem that had precipitated his public breakdown 56 years earlier, remained unproved. Nash was not the last brilliant mathematician to be consumed by this problem. Louis de Branche de Borsier is a mathematician at Purdue University who in 1985 proved the Bieberbach conjecture, a famous open problem in complex analysis that had resisted proof for 68 years. This was a real accomplishment, accepted by the mathematical community, and it established de Branche as a mathematician of serious and proven ability. But de Branche has also claimed, repeatedly, to have proved the Riemann hypothesis. He has been making this claim since the late 1990s. Updated versions of his proof, bearing titles like Apology for the Proof of the Riemann Hypothesis, have been posted to his Purdue faculty webpage for over 2 decades. The mathematical community has examined his arguments and found them unconvincing. In 2000, J. Brian Connery and Xianjun Li published a paper in the International Mathematics Research Notices, number 18, originating from an arXiv preprint in December of 1998, that specifically addressed the Hilbert spaces of entire functions framework de Branche has employed. They showed that the specific approach, while valid in the abstract, did not apply to the Riemann Zeta function in the way de Branche claimed. The framework could not support the conclusion. De Branche has disputed this and continued to post revised proofs. As of 2026, the mathematical community considers the matter settled. The proof does not work. There is something almost painful about de Branche's persistence. He is not a fool. He proved the Bieberbach conjecture. He knows what a correct proof looks like. But the Riemann hypothesis has a quality that other unsolved problems do not have. a seductive quality, a way of making you feel like you are one step away from the answer even when you are not. And de Branges has spent decades in that one step away feeling, unable to see that the last step does not exist. Then there is the story of Xianjin Li. In July of 2008, Li posted a paper to the Arxiv claiming a proof of the Riemann hypothesis using a different approach. Within days, experts including Terence Tao and Alain identified a fatal error. The gap in the argument was not subtle, it was structural. Li withdrew the paper. His experience illustrates something about the Riemann hypothesis that the slow accretion of partial results does not convey. The problem is deceptive. The landscape of possible approaches is littered with paths that look promising, paths that seem to lead somewhere and that end in sheer cliff faces, invisible until you are standing at the edge. Mathematicians who work on this problem describe a feeling of always being almost there, of the proof being almost in reach, and of the almost never converting to actually. And then there is the most public failure of all, and the saddest. On the 24th of September 2018, Michael Atiyah stood before an audience at the Heidelberg Laureate Forum in Germany and claimed he had proved the Riemann hypothesis. Atiyah was one of the most decorated mathematicians of the 20th century. He had won the Fields Medal in 1966 for his work in topology and algebraic geometry. He had won the Abel Prize in 2004. His Atiyah-Singer index theorem, proved with Isidore-Singer, is one of the towering achievements of modern mathematics, connecting analysis, geometry, and topology in a framework that has applications across every branch of the subject. He was 89 years old when he stood at that podium. His claimed proof was 5 pages long. It relied on a function he called the Todd function, named after his former teacher, J.A. Todd, which Atiyah connected to his work on the fine structure constant. Experts were skeptical from the moment the announcement was made. The paper was circulated and analyzed within hours. The consensus, expressed diplomatically but unambiguously by mathematicians writing for the A periodical and in private communications that quickly became semi-public, was that the proof was not valid. The argument contained gaps that could not be filled. The Todd function, as described, did not have the properties the proof required. Atiyah died on the 11th of January 2019, less than 4 months after the Heidelberg lecture. His earlier work is secure. The index theorem alone would place him among the greatest mathematicians of the 20th century. But his final public mathematicians of the Riemann hypothesis delivered before an audience that knew within minutes it could not work, by a man whose earlier career had been defined by proofs that worked beautifully. I think about these stories together, and I see a pattern that is about more than individual failure. Nash at Columbia in 1959, de Branges at Purdue decade after decade, Li on the Arxiv retracted within days, Atiyah at Heidelberg 5 months before his death. These are not cautionary tales about overconfidence. They are evidence of something about the nature of this particular problem. The Riemann hypothesis does not merely resist proof. It attracts proof attempts the way a flame attracts moths. It shows you structure. It shows you patterns. It shows you connections so deep and so beautiful that you become convinced the answer is within reach. And then it closes the door, and the people who get closest sometimes lose the most. The Riemann hypothesis is the only unsolved problem that appears on both Hilbert's 1900 list and the Clay Mathematics Institute's 2000 Millennium Prize list. That gives it a 126-year pedigree of being considered the single most important open problem in mathematics by 2 independent panels separated by a century. Of the 7 original Millennium Prize problems, only one has been solved, the Poincaré conjecture, proved by the Russian mathematician Grigory Perelman between 2002 and 2003. The Clay Institute offered Perelman the $1 million prize. He declined it. He also declined the Fields Medal. The Riemann hypothesis remains one of 6 unsolved Millennium problems. It is the oldest. It is the only one that predates the 20th century. And it is the one connected to the largest number of other mathematical results. There exists a running catalogue of theorems in mathematics that assume the Riemann hypothesis or the generalized Riemann hypothesis as a precondition. The count is in the hundreds. Hundreds of published results in number theory, algebraic geometry, cryptography, analytic combinatorics, and probability theory that are true if and only if the Riemann hypothesis is true. These are not speculative papers. They are established mathematics with the caveat assuming RH in the statement of the theorem. The mathematical community has been building on this unproved foundation for over a century, adding floors to a structure whose basement has never been inspected. But there is a result from 2018 that I have been saving because I think it may be the most unsettling piece of this entire story, and I want it to land with its full weight. In 1950, the Dutch mathematician Nicolaas Govert de Bruijn introduced a real parameter, now called lambda, associated with deformations of the Riemann xi function. The xi function is a modified version of zeta that has the same non-trivial zeros but better symmetry. De Bruijn showed that if you heat the xi function, if you evolve it forward in time using a specific heat equation, the zeros migrate. They slide around on the complex plane. And there exists a critical value of the time parameter, lambda, such that for all times less than lambda, some zeros lie off the critical line, and for all times greater than or equal to lambda, all zeros are on the line. De Bruijn proved that if lambda is less than or equal to 0, the Riemann hypothesis is true. 26 years later, in 1976, Charles M. Newman conjectured that lambda is greater than or equal to 0. If true, this would mean the Riemann hypothesis is true by the narrowest possible margin. The zeros sit on the critical line, but any perturbation, any positive amount of heating, would push them off. Newman himself said that his conjecture, if correct, would mean the Riemann hypothesis, if true, is only barely true. Think about what that phrase means. Only barely true, not robustly true, not securely true, not true with room to spare. True the way a coin balanced on its edge is upright. Technically, yes, but if you breathe on it, it falls. On January 18, 2018, Brad Rogers at Queen's University in Canada and Terence Tao posted a paper to the Arxiv proving Newman's conjecture. Lambda is greater than or equal to 0. The Riemann hypothesis, if true, is only barely true. The paper was published in Forum of Mathematics, Pi, Volume 8, in 2020. The result was tightened further by Polymath 1.5, a massive online collaborative mathematics project coordinated by Tao. In August of 2019, the collaboration established that lambda is at most 0.22. So the Riemann hypothesis is equivalent to saying lambda lies in the interval from 0 to 0.22. The truth has been squeezed into a narrow corridor, 0 on one side, 0.22 on the other. The Riemann hypothesis says lambda equals 0. The evidence says lambda is near 0, and the proof that it is exactly 0 does not exist. Every piece of evidence points to the Riemann hypothesis being true. Every approach, from every direction, number theoretic, spectral, computational, physical, converges on the same answer. The zeros are on the line, but the proof does not close. And here is where I want to raise the possibility that popular accounts of this problem almost never mention, and that the mathematical community discusses only reluctantly, and that I think may be the most important thing about the Riemann hypothesis that you were never told. The reason nobody has proved it might not be that the problem is hard. It might be that the problem is impossible. Not impossible in the sense that the hypothesis is false. The hypothesis is almost certainly true, but impossible in the sense that a proof may not exist within the standard framework of mathematical reasoning. In 1931, Kurt Gödel proved the incompleteness theorems, which are among the most important results in the history of human thought. The first incompleteness theorem says that in any consistent formal system capable of expressing basic arithmetic, there exist true statements that cannot be proved within that system. Not statements we have not proved yet, statements for which no proof exists, statements that are true but formally unreachable. The system can describe them, it can state them, it can even check individual cases, but it cannot prove the general claim. The Riemann hypothesis is a statement about natural numbers. Specifically, it is what logicians call a pi-1-0 statement, a universally quantified claim about integers that can be verified case by case. In 1976, Martin Davis, Yuri Matyasevich, and Julia Robinson showed that the Riemann hypothesis can be expressed as a Diophantine equation, a polynomial equation in integers. This places it squarely in the domain to which Gödel's theorems apply. The Riemann hypothesis could, in principle, be true for every zero, true for every case ever checked, and yet unprovable from the axioms of ZFC, the standard axiomatic foundation of mathematics. I want to be careful here. The consensus among working mathematicians is that the Riemann hypothesis is provable and will eventually be proved. Nobody in the mainstream believes it is undecidable, but nobody has proved that it is not undecidable. That possibility has not been eliminated, and the fact that 167 years of sustained effort have failed to produce a proof, while every conceivable kind of evidence has accumulated in its favor, is at minimum consistent with the hypothesis that we are not just looking for a key that is hard to find, but might be pushing against a door that does not open from this side. There is precedent. The continuum hypothesis, one of the other great problems of set theory, was shown to be independent of ZFC by the combined work of Gödel in 1938 and Paul Cohen in 1963. It can be neither proved nor disproved from the standard axioms. It is true in some models and false in others. The possibility that the Riemann hypothesis could join it in this category, true in some models, false in others, undecidable from the axioms that underpin virtually all of modern mathematics, is a possibility that the mathematical community has not ruled out and cannot rule out with current methods. And if the Riemann hypothesis is undecidable, the consequences would ripple through mathematics in a way that is difficult to overstate. Every theorem conditional on RH would be permanently suspended. Not false, not wrong, just forever unresolved. Miller's deterministic polynomial time primality test, which requires the generalized Riemann hypothesis, would never be unconditionally certified. The sharpest error bounds in the prime number theorem would remain conjectural in perpetuity. Entire branches of analytic number theory would exist in a permanent state of incompleteness, their deepest results resting on a foundation that can never be verified and never be refuted. But I think there is a consequence more unsettling than the practical ones. If the Riemann hypothesis is true but unprovable, it means the primes have a structure, a deep, precise, verifiable structure that mathematics can describe but cannot explain. We can see the pattern. We can check it case by case to arbitrary precision. We can hear the music, but we cannot prove why the orchestra plays in tune. The numbers would know something that we cannot know. Mathematics would contain a truth about its most fundamental objects that is beyond the reach of mathematical proof. I want to address one more angle before I close, because it is the one most commonly attached to this problem in popular accounts, and it is mostly wrong, and the way in which it is wrong is itself interesting. You have probably heard that the Riemann hypothesis is connected to internet security. The standard version goes like this. RSA encryption depends on the difficulty of factoring large numbers into primes. If the Riemann hypothesis were proved, we would understand primes well enough to crack RSA, and the internet would become insecure. This is not true. RSA security rests on the computational hardness of factoring. Proving the Riemann hypothesis would sharpen our understanding of how primes are distributed, how they thin out, where the error in the prime number theorem lies. It would not provide an efficient algorithm for factoring a specific large number into its prime components. The genuine threat to RSA comes from quantum computing, specifically from Shor's algorithm running on a fault-tolerant quantum computer, and that is entirely independent of the Riemann hypothesis. But the part of the cryptography story that is true deserves attention. The generalized Riemann hypothesis, an extension of Riemann's conjecture to a broader family of functions called Dirichlet L functions, is assumed in the proof of several foundational results in computational number theory. Gary Miller's deterministic primality test, published in 1976, requires the generalized RH. Without that assumption, the algorithm's correctness cannot be guaranteed. Other results, about the distribution of primes in arithmetic progressions, results used in the generation and certification of the large primes that underpin cryptographic key generation, similarly depend on the generalized RH. The upshot is this. Parts of the mathematical infrastructure that supports modern cryptography sit on top of a conjecture that has never been proved. This was done because the conjecture is overwhelmingly likely to be true, but it is still, formally, an unproved assumption. And if it is wrong, the consequences would cascade through computational number theory in ways that are difficult to predict. And if the Riemann hypothesis were actually false, if someone found even one zero with real part not equal to 1/2, the consequences would be seismic. Every conditional theorem would collapse. The error term in the prime number theorem would be worse than assumed. The primes would contain a hidden disorder that has evaded 3 trillion checks. And the random matrix connection, the deep bridge between number theory and quantum physics that Montgomery and Dyson discovered, would crack. The GUI statistics depend on the zeros being on the critical line. A single exception would not just disprove a conjecture. It would sever the most mysterious link between mathematics and physics that anyone has ever found. Nobody expects this. The evidence is too strong, the connections too deep, the verification too extensive. But nobody can prove it cannot happen either. I want to go back to the mathematics for a moment, because I think there is an aspect of the Riemann hypothesis that gets lost in the stories of failed proofs and million-dollar prizes. And it is the aspect that I personally find most difficult to stop thinking about. The explicit formula. The one Riemann wrote down and von Mangold made rigorous. The formula that says the prime counting function pi of x equals a smooth main term, the logarithmic integral LE of x, minus a sum over all the non-trivial zeros, plus some small correction terms. Every zero contributes a wave. Every wave has an amplitude and a frequency. The frequency is determined by the imaginary part of the zero, how high it sits on the critical line. The amplitude is determined by the real part. If all zeros have real part 1/2, every wave has the same amplitude. The corrections to the smooth main term are all of the same size, proportional to the square root of x. They oscillate, they interfere, they partially cancel each other out. The result is that the primes stay close to their expected positions. The error in the prime number theorem is controlled. The primes are as orderly as they can be given that they are, after all, individual discrete points and not a continuous curve. But think about what that means in terms of the zeros themselves. There are infinitely many of them. The first is at height 14.13, the second at 21.02, the 100th is around 236.5, the 10,000th is around 9,877. They keep climbing, getting denser, packing closer and closer together as you ascend the critical line. And every single one of them, without exception, chooses to sit at real part 1/2. Not one deviates, not by a billionth, not by a trillionth, not by any amount. Why? That is the question at the bottom of everything. Not, is it true? We know it is almost certainly true. The question is why? Why do the zeros line up? What forces them onto the critical line? What structure in the zeta function? What property of the primes? What feature of the number system itself compels every single zero to sit at exactly real part 1/2? And we do not know. 167 years of effort, and we do not know. The Hilbert-Polya conjecture says the answer is spectral. The zeros are eigenvalues of an operator, and the operator forces them onto the line. But we do not have the operator. The Berry-Keating conjecture says the answer is quantum mechanical. The zeros are energy levels of a quantum system, and the quantum system forces them onto the line. But we do not have the quantum system. The random matrix connection says the zeros behave like eigenvalues of random matrices, but random matrices are descriptions of statistical behavior, not explanations of why that behavior occurs. We have descriptions, we have matches, we have analogies so precise they amount to identities, and we do not have a reason. I spent weeks reading about this, reading the original papers, reading the biographies, reading the failed proofs and the successful partial results, reading Conz's 2026 survey, where he reconstructs 50 zeros from 5 primes, reading Hardy's memoir and Selberg's laconic papers and Odlyzko's computational summaries. And the thing that sits with me, the thing I cannot shake, is not any particular mathematical result. It is the feeling that the Riemann hypothesis describes a feature of reality, not just a feature of mathematics. The primes are real. I do not mean they exist in some abstract, Platonic heaven. I mean they are operative. They are the building blocks of every integer. Every integer factors uniquely into primes. The number of atoms in the observable universe factors into primes. The number of seconds since the Big Bang factors into primes. Every measurement you have ever made, every distance you have ever traveled, every dollar you have ever spent, when expressed as an integer, breaks down into primes. They are not theoretical constructs. They are the skeleton of the number system, and the number system is the skeleton of quantitative reality. And those primes, those real, concrete, operative objects, are controlled by zeros on a line in the complex plane. Not metaphorically, literally. The explicit formula is not an analogy. It is a precise mathematical identity. The primes are where they are because the zeros are where they are, and the zeros are where they are for reasons we cannot explain. There is a phrase that Alain used in one of his lectures that I have been thinking about since I first encountered it. He compared the Riemann zeta function to a musical instrument and the zeros to its resonant frequencies. He said the primes are the sound produced by the instrument. And then he said something that lodged in my mind and has not left. He said that what mathematicians are trying to do is not just describe the sound or list the frequencies, but find the instrument, the physical object that produces the music, the operator, the quantum system, the thing that vibrates at exactly the right frequencies to produce the prime numbers. And we have been looking for that instrument for 167 years. We can hear the music perfectly. We can transcribe every note. We can identify every frequency. We can verify that every frequency falls on the critical line to arbitrary precision. But we cannot find the instrument. We cannot prove it exists. We cannot prove it does not exist. The music is playing, and we cannot find the source. And I want to take a moment to describe what the zeros actually look like, because most accounts of the Riemann hypothesis treat them as abstract mathematical objects, points in a plane that satisfy an equation. They are. But they are also something you can visualize, something you can almost feel if you spend enough time with the data. Imagine a vertical line in a two-dimensional plane. The horizontal axis is the real part of a complex number. The vertical axis is the imaginary part. The critical line sits at real part 1/2, running straight up and down through the plane. Now imagine dots on that line. Each dot is a non-trivial zero of the zeta function. The first dot is at height 14.13. The second is at 21.02. The third at 25.01. They are spaced unevenly. The gap between the first two is about 6.9. The gap between the second and third is about 4. As you go higher, the gaps on average get smaller. The zeros get denser. By the time you reach height 1000, the average gap between consecutive zeros is about 1.09. By height 1 million, it is about 0.45. By height 10 to the 20th, where Odlyzko was computing, the average gap is so small that the zeros are packed like grains of sand, each one at real part exactly 1/2. Their imaginary parts climbing the line in an increasingly tight procession. But the gaps are not uniform. That is the key thing. The average gap shrinks, but the individual gaps fluctuate. Sometimes two zeros sit almost on top of each other. Sometimes there is a slightly wider gap, and the statistical pattern of those fluctuations, the way the gaps are distributed around their average, is the pair correlation that Montgomery computed and Dyson recognized. It is the same distribution as the spacings between eigenvalues of random Hermitian matrices. This means the zeros repel each other, not literally, not physically, but statistically. Two zeros are less likely to be very close together than they would be if they were distributed randomly. They space themselves out as if each zero is aware of the positions of its neighbors and adjusts accordingly. This is the same behavior exhibited by energy levels in quantum systems. In nuclear physics, the phenomenon is called level repulsion. Energy levels of a heavy nucleus do not cluster randomly. They push each other apart. And the Riemann zeros do the same thing. Same statistics, same repulsion pattern, same mathematics. If you were to listen to the zeros as sound, if you mapped each zero's height to a frequency and played them simultaneously, what you would hear is not noise and not a pure tone, but something in between. A structured hum, a sound with a specific texture, a specific character, a character that physicists recognize as the signature of a quantum chaotic system. The zeros sound like a heavy atomic nucleus. The primes sound like quantum mechanics. And nobody knows why. I want to ground this in something concrete, because the connection between prime numbers and daily life is closer than you might think. And I think that proximity makes the mystery more, not less, unsettling. Every time you visit a website that uses HTTPS, the padlock icon in your browser, your computer exchanges cryptographic keys with the server. Those keys are generated using large prime numbers, typically primes hundreds of digits long. Finding those primes requires algorithms that depend on the distribution of primes, specifically on how common primes are in a given range of numbers. The prime number theorem tells you approximately how many primes exist below a given bound. The Riemann hypothesis tells you how much the actual count can deviate from the approximation. If the Riemann hypothesis is true, the deviation is small, bounded by the square root. If it is false, the deviation could be larger, and our estimates of prime density could be off in ways that would affect the efficiency, though not necessarily the security, of prime generation algorithms. Every time your phone encrypts a message, every time your bank processes a transaction, every time a certificate authority signs an SSL certificate, the primes are there, behind the glass, doing the work. And the law that governs where they fall, how dense they are, how they cluster and thin out, is the law that the Riemann hypothesis describes and that nobody has proved. And here is where the emotional weight of the problem becomes, I think, qualitatively different from other unsolved problems in mathematics. Other Millennium Prize problems are important but specialized. The Yang-Mills mass gap is about quantum field theory. P versus NP is about computational complexity. The Hodge conjecture is about algebraic geometry. These are deep problems, but they live in specific rooms of the mathematical house. The Riemann hypothesis lives in the foundation. It connects to number theory, complex analysis, probability theory, random matrix theory, quantum mechanics, spectral geometry, non-commutative geometry, and the foundations of logic. It is not a problem that sits in one room. It is a crack that runs through the basement. And the people who work on this problem know it, not in the way that they know other open problems are important, in a way that is closer to how a doctor knows that a patient's condition is serious. The Riemann hypothesis is not just an intellectual challenge. It is a gap in our understanding of the most basic objects in mathematics, a gap that has persisted for longer than anyone alive has been alive, that has survived every technique ever thrown at it, and that may, in principle, be permanent. I spoke earlier about the psychological effect of this problem on the people who work on it. Let me add one more dimension to that picture. There is a phenomenon in mathematics that does not have an official name, but that anyone who has worked on hard problems recognizes. It is the feeling of being close, of seeing the structure clearly enough to describe it, to verify it, to feel its shape in your hands, but not clearly enough to prove it. This feeling is addictive, and it is treacherous, because the clarity you feel may be genuine, understanding, or it may be an illusion. And in the case of the Riemann hypothesis, 167 years of history suggest that the feeling of being close is not a reliable indicator of actually being close. Every generation of mathematicians has believed that the tools of their era were sufficient, or nearly sufficient, to settle the question. Every generation has been wrong, and the feeling of proximity persists because the evidence keeps getting stronger, the connections keep getting deeper, and the proof remains exactly as far away as it was when Riemann put down his pen. There is something about that image that I find genuinely unsettling, not in the way that horror movies are unsettling, with their manufactured dread, in a quieter way, in the way that looking at the night sky and trying to feel the distance to the nearest star is unsettling. The primes are the most basic objects in mathematics. 2, 3, 5, 7. You learn them in elementary school. You factor numbers into them. You use them to reduce fractions. They are the most familiar mathematical objects that exist, and they are governed by a law that nobody can prove, that nobody can explain, that connects to quantum physics and random matrices and non-commutative geometry, and that has resisted the collective effort of the entire mathematical community for longer than any person alive has been alive. Enrico Bombieri, the Fields medalist who perpetrated the 1997 April Fool's hoax, once described the emotional pull of the Riemann hypothesis in a way I found unexpectedly honest. Bombieri sent an email on the 1st of April 1997 to colleagues claiming that Alain and a young physicist had solved the Riemann hypothesis using methods from string theory. The email was forwarded through the mathematical community at what was for 1997 an extraordinary speed. It reached major departments on multiple continents within hours. Mathematicians who should have known better, who should have checked the date, read the email and felt their hearts accelerate. For a few hours, the possibility that the greatest unsolved problem in mathematics had fallen was taken seriously by serious people. It was a joke. Bombieri confirmed it later that day, but the reaction tells you something about the gravitational pull of this problem. Even as a hoax, the prospect of a proof of the Riemann hypothesis is enough to stop the mathematical world. Everyone who works in number theory carries this problem. It is the background radiation of the field. It hums in every paper, every computation, every assumption that begins with conditional on the Riemann hypothesis. It is the thing that everyone knows might be true and nobody can prove is true, and that pervades the subject like a scent you cannot identify and cannot ignore. I want to come back now to the man who started this, because I think the biography, held up against the mathematics, tells a story that neither one tells alone. Bernhard Riemann was by every account a man of extraordinary internal depth and almost crippling external limitation. He could not speak to a crowd without anxiety. He suffered from chronic illness. He lived in poverty. He married late, had one daughter, and spent the last 4 years of his life shuttling between Göttingen and Italy, trying to find air his lungs could tolerate. He was, in almost every external measure, a fragile person. And internally, he was one of the most powerful mathematical thinkers who has ever existed. His doctoral thesis redefined complex analysis. His habilitation lecture replaced Euclidean geometry with something so general that it became the mathematical language of general relativity. His contributions to the theory of integration are still taught in every calculus course, and his 8-page paper on prime numbers, written as a brief memoir upon his election to the Berlin Academy, opened a window into the structure of the integers that the entire field of analytic number theory has spent 167 years trying to see through clearly. The gap between the man and the legacy is something I keep returning to. He was 33 when he wrote the paper, 39 when he died. He produced mathematics of such depth and originality that it took decades for the rest of the field to understand what he had done. His geometry waited 60 years for Einstein. His Zeta function waited 167 years and counting for a proof. And the papers that were lost after his death, I keep coming back to those. Dedekind salvaged what he could and published the collected works in 1876. But there were losses. The historical record is clear on that. Even if the details, the housekeeper, the fireplace, the careless sorting remain uncertain. Somewhere in the material that did not survive, there may have been fragments, approaches, calculations, intuitions about the zeta function and its zeros that could have shortened the search by decades. We will never know. There is a cruelty in the timeline that I think gets overlooked. Riemann wrote his paper in 1859. He died in 1866. The prime number theorem was proved in 1896 using his methods 30 years after his death. Hardy proved infinitely many zeros on the line in 1914, 48 years after his death. Montgomery discovered the random matrix connection in 1972, 106 years after his death. Cornes gave the spectral interpretation in 1999, 133 years after his death. Platt and Trujian verified 3 trillion zeros in 2021, 155 years after his death. Cons reconstructed 50 zeros from 5 primes in 2026, 160 years after his death. Each of these results is a partial answer to the question Riemann raised in 8 pages and then died before the world could pursue. Each one goes deeper. Each one confirms what he conjectured, and none of them close the gap. The question he asked in 1859 is the same question we are asking in 2026. Are the zeros on the line? We think so. We are nearly certain, and we cannot prove it. Riemann's last day was the 20th of July, 1866. He was sitting in a chair under a fig tree near the house in Salaska, looking out over Lake Maggiore. His wife Elise was with him. His health had been declining for months. He had come to Italy because the northern Italian climate was supposed to be better for his lungs than the damp cold of Göttingen, and for a time it was, but by July the tuberculosis had progressed past the point where climate mattered. He worked on mathematics until very near the end. The exact content of his final calculations is unknown. He recited the Lord's Prayer with Elise, completed it, and died. He was 39 years old. He left behind a reshaping of geometry that would not be fully appreciated for 60 years. He left behind a reformulation of complex analysis that remains standard today. He left behind an 8-page paper about prime numbers that would become the most famous unsolved problem in mathematics and would resist the combined efforts of every generation of mathematicians from 1859 to the present day. And he left behind lost papers, notes, drafts, calculations, ideas that Dedekind could not recover and that no one else could reconstruct, fragments of a mind that saw deeper into the structure of numbers than any mind before or since, lost to history because a 39-year-old man died of tuberculosis in 1866, and somebody, whether a housekeeper or a colleague or the simple entropy of a wartime university, allowed the papers to scatter. If I had to choose a single image to capture what the Riemann hypothesis means, it would not be the critical line, it would not be the zeta function, it would not be the explicit formula, or the random matrices, or the spectral interpretation. It would be those lost papers, because the Riemann hypothesis is, at its core, a statement about something we can see but cannot fully reach, a pattern we can verify but cannot prove, a truth we can describe but cannot explain. Like papers you can almost read through the flames, close enough to see there are words on the page, too far away to make out what they say. The zeros are on the line. I believe that. Every mathematician I have ever read on this subject believes that. The evidence is overwhelming. The connections are too deep. The computations too extensive. The structural arguments too coherent. The Riemann hypothesis is true. Almost everyone in the field would bet their career on it. Many have. But the proof is not there. It has been 167 years. The proof is not there. Hardy proved infinitely many zeros in 1914. He died in 1947. The proof was not there. Selberg proved a positive proportion in 1942. He died in 2007. The proof was not there. Levinson proved a third in 1974. He died in 1975. The proof was not there. Conry proved 40% in 1989. He is still working. The proof is not there. Platt and Trujian verified 3 trillion zeros in 2021. The proof is not there. Tao proved the de Bruijn-Newman constant is at least 0 in 2018 and helped squeeze it below 0.22 in 2019. The proof is not there. And there is a version of reality, consistent with everything we know about the foundations of mathematics, in which the proof will never be there, in which the primes have a structure that is true and verifiable and connected to the deepest architecture of both mathematics and physics, and that is beyond the reach of any proof that any human or any machine or any formal system humans can construct will ever produce. The numbers know. They have known since before there were mathematicians to wonder, since before there were languages to ask the question, since before there were minds to formulate conjecture. The primes fall where they fall because the zeros sit where they sit. On the line, all of them, always. A man saw this in 1859. He wrote it on 8 pages. He died at 39 with the Lord's Prayer on his lips and his wife beside him and Lake Maggiore outside the window. And the greatest unsolved problem in mathematics, unsigned and unfinished in the papers on his desk. 167 years later, the rest of us are still reading those 8 pages, still checking the zeros, still looking for the proof, still looking for the instrument that plays the music of the primes. And the primes keep going. They do not wait for us. They do not need our proof. They do not need our understanding. They were prime before we counted them. They will be prime after we are gone. And whatever holds them to their pattern, whatever law puts every zero on that line, whatever structure lies at the bottom of arithmetic itself, it was there before the universe had stars. And it is still unproved. I want to say one more thing, because I have been thinking about it the entire time I have been working on this, and I do not think it gets said enough. There is a version of this story that treats the Riemann hypothesis as a puzzle. A hard puzzle, certainly. The hardest puzzle in mathematics. But still a puzzle, something with a solution that we simply have not found yet. Something that human cleverness will eventually crack, the way it has cracked every other mathematical problem that was once considered impossible. Fermat's last theorem resisted proof for 358 years until Andrew Wiles proved it in 1995. The Poincaré conjecture resisted for 99 years until Perelman proved it in 2003. The history of mathematics is a history of impossible problems eventually being solved. But the Riemann hypothesis is different. I think it is different. Not because it is harder, though it may be harder, because of what it means. Every other major conjecture, once proved, tells you something new about the objects it describes. Fermat's last theorem told us that the equation x to the n plus y to the n equals z to the n has no positive integer solutions for n greater than 2. That is a fact about numbers. Once proved, it is settled. The objects were always this way. The proof reveals what was always true. The Riemann hypothesis, if proved, would tell us something we already know. That the zeros are on the line, that the primes are orderly, that the error term is bounded by the square root. We know all of this from computation and evidence. What a proof would give us is not new information about the primes. It would give us a reason. It would give us the why. Why do the zeros sit on the line? What forces them there? What structure in the number system, what deep architectural principle of arithmetic compels every zero of the zeta function to have real part exactly 1/2. And if the proof never comes, we will have something unprecedented in mathematics, a truth without a reason, a pattern without an explanation, a fact about the most fundamental objects in mathematics that mathematics can verify, compute, test, and confirm to any degree of precision you care to name, but cannot explain. I think that possibility is more consequential than the proof itself would be, because it would mean that the relationship between truth and proof, the relationship that defines mathematics, the relationship that makes mathematics different from every other form of human knowledge, is not what we thought it was. We thought truth and proof were the same thing in mathematics. We thought that if something was true in mathematics, it could be proved. Gödel showed in 1931 that this is not always the case. But Gödel's examples were artificial, constructed specifically to demonstrate the incompleteness. They were logical curiosities, not mathematical necessities. If the Riemann hypothesis is true and unprovable, it would be the first natural example. The first time a statement that mathematicians actually care about, that has real consequences, that connects to physics and cryptography and the deepest structures in analysis and number theory, turns out to be beyond the reach of proof. That would change mathematics, not the practice of it perhaps. Mathematicians would continue to assume RH, as they have for over a century, and they would continue to build on it. But the philosophy of mathematics, the understanding of what mathematical knowledge is and what it can achieve, would shift. Mathematics would no longer be the domain of absolute certainty. It would be the domain of almost certain certainty, close enough for practical purposes, but not perfect, not complete, not what it was supposed to be. And the man who opened this possibility, who cracked the foundation with 8 pages and a 4-word hedge, it is very probable, is buried in the Stadtfriedhof Cemetery in Göttingen, Germany. He died in Italy, but his remains were brought back to Göttingen, the university town where he had spent most of his working life, where Gauss had supervised his thesis, where he had delivered the habilitation lecture that rewrote geometry, where he had been elected to the faculty, and where the papers that might have explained everything were lost after his death. His grave is modest. The inscription records his name, his dates, and nothing else. The greatest unsolved problem in mathematics does not appear on his tombstone. The 8 pages that changed number theory forever are not mentioned. Just a name and 2 dates, 1826 to 1866. 39 years, 15 of them as a working mathematician, 8 pages on prime numbers, a conjecture 4 words long, and 167 years of consequences still unfolding. The zeros sit on the line, 3 trillion checked and counting. The evidence is overwhelming. The connections are deep. The mathematics is beautiful. The proof does not exist. It may never exist. And the primes keep going. Out past the numbers we can compute. Out past the numbers we can name. Out past anything the human mind can conceive of as a quantity. They thin out, logarithmically spaced, ever wider, governed by the zeros of a function, written on 8 pages in 1859, by a man who saw something in the structure of numbers that nobody else could see, and who died before the world understood what he had found. The numbers know why the zeros are on the line. They have always known. They do not need a proof. They do not need a reason. They do not need us. And whatever they know, it was old before the universe had stars, and it will be true after the last star burns out, and it is still unproved.